Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session we are going to do a pipe weep simulation, and in this particular simulation the scenario is the power point 2 cross pipelines, and the top line got ruptured, so there is a sudden release of fluid and it just pipe rotated about this support point and it goes and hit the bottom point. So bottom pipe both end are fixed, support condition fixed, and the top pipe sudden release of fluid, it's a broken rupture, so it go and hit on the bottom pipe. So it's pipe weep simulation what we are going to do. The other things what we are going to do is look into energy balance, how the energy balance is there, because this particular high deformation impact problem, there are chances you may get a lot of hourglass. So how to control the hourglass, looked into how the overall simulation looks, whether it is results are accepted or not, how much hourglass energy is generated. So all those things will look. So this problem we are going to do in today's session. The learning in this problem is how to look into energy balance. Then the top pipe is hitting the bottom pipe with a rotational angular velocity. So how to give a rotational velocity to the component, which is also important in this simulation. So we'll learn this and we'll try to solve this problem. Now before going to start this problem, let's quickly look into what we are going to do. We are going to do a pipe weep simulation in Abaqus Explicit, so it will be dynamic explicit case. The example simulates is a pipe on pipe impact resulting from a rupture of a high pressure line in power plant. It is assumed that sudden release of the fluid could cause one segment of pipe rotate about support and strike a neighboring pipe. So the red color is a pipe where there is a sudden release of fluid, and its one end will be pin condition, other will be free. So about that pin location, the support condition, is going to rotate. So the rotational velocity is like a 75 radians per second. With that velocity, it's going to hit the bottom pipe where the both end is the end caster condition fix. Typically these pipes are 45 ksi steel pipe. So the typical 70.85 e power minus 0 ton per millimeter cube is a mass density. Modulus will be 210 e power 03 MPa. 0.3 will be Poisson's ratio. 75 ksi steel means around 310 MPa is the yield, and 450 is the point where the plastic strength will be 80%. So you get a tangent modulus out of this. The unit which we are going to follow is a ton millimeter Newton second SI units. So this OD of this is a 168.275, length is 1270, thickness is 10.95. So from OD ID you can calculate what is a mid surface. So we are going to model a mid surface in this case. So let's start doing this problem. So let me clear this and let me set the directory. So my directory is set. So we'll quickly create a bottom pipe. It's deformable 3D shell extrusion. I'm going to put 0, 0. Then I'll just take and then create a circle. Now we are going to make this in on a mid surface. So I already calculate what is the radius for the mid surface. So the radius for the mid surface is 78.6525. It is like you calculate OD, you know the thickness, so you get a ID. So OD plus ID divided by 2, so you'll get a mid surface diameter, and from that you can calculate this radius. So we are done that. Now we'll just extrude it by 1270. I'll cut this along the length at the half, and then central also I'll cut. So I'm going to put XY at the mid plane, so mid center. So 635 is the mid. Total is 1270. So half will be 635. Then I'll put also one plane xz at 0 0. So that I done. Then I'll just quickly cut it. So I want to select this, so it is half. Then I'll select both, and then I'll select this and trim it. So that way I get a this is better for me to put mesh and then create a pin condition, rotational velocity. This is a good thing. That's the reason I cut it. Now since the both pipe is same dimension, I can make a copy of this, and I can say at top pipe, and since we both are done, so I'll just quickly create an instant, and that way we can just try to rotate it and then shift it. So first we'll just move it. Top pipe will move it by I already calculate what is a mid diameter, so it is 157.305. so I'll put 0 0, then I'll put 0 comma 157.305 comma 0. So my pipe is, if I looked, let me put in some viewpoint. So they are just in touching condition. Now I'll still move it up by because this is not mid surface, so if they are to be just in perfect touch, the gap between these two is the half of the thickness of the top and half of the thickness of this. So thickness is 10.97, so it should be at 10.97. so I'll further move the top pipe by, the starting point is this, then top is 10.97 comma 0. so it just gone to the top. So now we got this both each other, but we want to have at a 90 degrees, so I'm going to rotate this. So we'll just going to rotate the top instant. Now we are going to it rotated by this center, so I'm going to select this point, and then I'll select this point. So about this 90 degree, and so now we got in, both are in good position, so it is touching and then both are 90 degree rotated. Now what we'll do, we'll quickly create a property, steel. We need to put a density because this will be on Abaqus Explicit, so dynamic explicit problem, so density is required for the mass matrix. Then we'll put 210 power e power 03 MPa and then 0.3 Poisson's ratio. We'll have a plasticity data, 310 is a yield, and then we'll put at a 450 around 0.8. Now we'll quickly create a thickness. So thickness is 10.97. Steel integration 0.5. Thickness integration Simpson we have, we'll select Gauss, and then now we'll just quickly assign this to the top pipe. It will be mid surface, so we just assign that. Now same thing we'll assign to the bottom pipe also. Mid surface, so we almost done both. So we'll quickly put a mesh on this. Mesh will put in part. So bottom pipe we are going to, for this the best thing is sweep. You get a quite a good mesh, and then we'll put a 10 millimeter. You can have finer mesh also, so 10 millimeter good. We'll also assign the elements for this is explicit S4R, and this is important. So Hourglass control, we are going to use enhance hourglass. So we have done that. Top plate will go, we'll also select the same sweep for this. This will be S for R explicit, and we'll say enhance 1, and then this also will put 10, and then we'll mesh it. So we have both top and the bottom pipe. Now couple of things we'll do. We'll just create a node set for the bottom pipe, both end. We'll just create fixed end. We're going to put boundary condition there. So we'll select by feature edge, and I'll put shift and put a shift key so you can select both. So done, we are done this. We'll select a top pipe. Now for top pipe, before putting anything, we'll just put a reference point here, because we are going to put a pin condition there. So we put a reference point there. Now top pipe will create a set. So node set, we're going to create this side tie node. So this point we are going to with this rigid reference point, we are going to tie it, and we are going to give a pin condition here. So we have done a set for that. Now one more set will create top nodes all. So this will be good for us to give a rotational velocity. So I selected all. So now I will go to first that pin location will just tied it. So we'll create a constraint rigid body, and we are going to put a tie connection. We are going to connect the top pipe tie, so they are there, and then we are going to select this point. Select reference point and say okay. So you see this about this point, these nodes are actually tied. Now we'll just put a go to the load. We'll quickly put a boundary condition. So one will be end caster. So we are going to select both end. We are going to put end caster, so we have put there, and then other is a pin condition, which will be on this point. So we are going to put pin condition there. So this created a pin condition. Now we are given a boundary condition, everything. Now other thing is we have to define a contact. Friction between these two is 0.2, and then you give a rotational velocity. So learning will be how you will give a rotational velocity, that is important. So we quickly create a friction. So tangential behavior, penalty based friction 0.2. We'll define a general contact Abaqus Explicit, and then we'll connect that friction there. So contact is defined. Now we have to give is a pre-described condition there. So now this is learning, guys. This is important step. So what I'm going to do, I'm going to go to query. Now this is important. I just want to apply a rotational velocity. So if I select this first point and this second point, then I have to put my right hand thumb along this direction. So along this direction, if you keep your thumb and rotate it out your forefinger in about that thumb, so that is a direction where the rotational velocity is going to take. So I am going to put query. So I'm going to select distance between this and this. So my first point is minus 635 160.630 and other is this side. So I'm going to put these 2 points for the rotational velocities. How to give a rotational velocity, that is important. So first we have to get 2 points. So if I put a thumb along my right hand thumb from this point to this, so thumb towards this direction, and then I rotate my finger, that will be the rotational velocity about this vector. So this is the perfect rotational velocity, so it's going to impact on this the bottom pipe. So I go to the prescribe one, create. Now rotational velocity. So velocity, then we are going to select all the nodes of the top pipe. Continue, we are done. So this will be rotational only. 75. Why positive 75? Because we are going to give this first point, second point is this. If I take first point this and second point this, then your thumb will be from pointing this to this. Then if you rotate finger, then you have to give a negative rotational vector here. But now since we are selecting this as a first point, this as a second point, so it will be positive 75 will go down. So the first point we are going to select from here. The second point we are going to select from here. So this is about this point, this arrow, right hand thumb put along this and then rotate your finger, that is negative Z. So we have done all these things. So we mesh, we given boundary condition, pin condition, then fix condition. Now we'll create a step. So it will be pipe whip. So we are going to select dynamic explicit, annual jump on. We are going to run for 15 millisecond. So done. So let's create a job. And let's do a data check. So submitted for data check. So just gone to data check. So no issue with data check, it's successful done. So we'll just submit it now for run. So once results is out, we can check. So we'll just check results, how far it has gone. So let's so simulation is going on. So now you see it's still not end, it is just pipe started hitting it. So and then you see the stress is also going up. And then its pipe is also getting, the bottom is also getting bent. This is almost high stress at the contacting point. So let me put in some, so let's look how it looks like. So top pipe it's bent, and at the center then you see the bottom pipe is also bent. So still it's going on, so let's check how far it has gone. So it's just done. So we got a result out, and we're just looking into the stress pattern, and the high stress is in that contacted region. It's almost gone to 400. Now let's look into energy point of view, whether the end time was sufficient. So go to XY plot, you say history output. Artificial strain energy is corresponding to hourglass. Internal energy is your elastic plus plastic strain energy, then you have kinetic energy, and then you looked into total energy. So if I plot it, so total energy is constant. First just it's hit, not immediately, but after some time it hit. So the kinetic energies go down, and then your internal energies goes up. Then around 11 millisecond it is kinetic energy is going back, so it is just bit a rebound of this. So all the maximum energy is gone into this kinetic internal energy, and then it is rebound bound. So the time is sufficient. So I think this is a good learning. Now learning what you get is out of this is how to give a rotational velocity, then vector, then right hand thumb rule, looking into energy, use of enhance hourglass control for this. So I guess this tutorial was example was helpful for you for dynamic explicit point of view step, also Abaqus explicit rotational velocity and enhance hourglass control. So if you like this video, don't forget to like us or subscribe us. Thank you, bye bye. Go ahead and have a happy learning. Thank you, bye bye.